In the following 10 minutes, I will give you an overview on how we deal with large amounts of time series data. We will explore the challenges and best practices on handling large amounts of time series data flowing in Ignition and being stored in a relational database. We will dive deeper into how we store the data, how we optimize access speed, and the best practices for managing the data along the way. Now let's start simple. Here we have an Ignition server connected to devices and clients. We have time series data flowing from the devices, and we see the current values in data points called tags in Ignition. And we use those real-time values at different screens. And now we need a place to store the historical data, or even a place for storing configuration data as reference data, metadata, some static data, transactional data, alarms, or maybe user interactions. And here now we involve a relational database. From now on, we can expand a project to bring a whole process together. And every database connection is configured in the Ignition gateway, where we can add a connection to a relational database management system as Postgres, MySQL, Microsoft SQL Server, Oracle, or any other supporting the Java database connectivity driver. And connecting a database to Ignition is done all by the Ignition gateway, and we can add as many connections as needed. And after we have connected Ignition to a database, we can start storing the historical data. And the bare minimum for storing historical data from Ignition is the tag historian module. This module provides storage and retrieval of historical data through the Ignition's tag system. And incoming data points are piped to the database and retrieved again through the module. And this is again configured all from the Ignition gateway. And the next question that we will answer is how we store the data. Now, if we imagine that we store the historical data in a single table in the database, we will face challenges as this single table will grow infinitely, leading to slow data retrieval. And this is where partitioning comes into play. Partitioning basically allows us to divide incoming data from Ignition into specific tables referred to as partitions based on a condition providing scalability. And we use horizontal branch partitioning to achieve this. And instead of storing all the data in a single table, we create separate tables depending on a time period, as in this simple example where we have 3 monthly partitions. And Ignition Stack Historian automatically creates the partitions and automatically stores data into separate tables based on the settings that we configure under the Ignition gateway. And under those settings, we provide the partitioning size. And the partitioning size plays a crucial role in the overall performance. If the partition size is too small, it may result in large amounts of partitions, in querying or analyzing data across multiple partitions requires operations such as join or union, which are expensive SQL operations, and they lead to performance overhead. On the other hand, if the partition size is too large, it may result in larger partition sizes that can impact data retrieval and analysis performance. We use rule of thumb, which states do not exceed 100 million rows per partition. And additionally, not only that we can enable tag historian, but we can also enable data pruning, and all data can be pruned to maintain system performance. And we can configure data pruning again in the Ignition gateway, and data older than the specified time period will be deleted. The configuration for data partitioning and data pruning again is done through the ignition gateway, and not SQL knowledge is needed to configure this. Same as the tag historian, we have additional systems within Ignition which utilize a database connection. And one of the advantages of using such system as the tag historian or the alarm journal for storing alarms, the database user source for storing user interactions is that the queries are automatically generated. And these systems are easy to set up and use as they are automatically generating the necessary tables, they automatically insert relevant data, and even provide pre-built tools for data extraction. And now we have the partitions in place, but the next challenge is the data retrieval. And basically, if we want to retrieve 3 months or 6 months or even 1 year raw data, that means that we need to retrieve millions of rows and visualize that, for example, in a chart in Ignition. And we want to see and be able to do that immediately. And that means that we need to reduce the processing overhead. The first step of achieving this is using preprocessed partitions. Preprocessed partitions are again automatically generated from Ignition, and here we basically duplicate the amount of partitions. And in the first set, we have the partitions with raw data, and the second set are the preprocessed partitions containing aggregations done over the raw data. Aggregations in the preprocessed partitions are done on a window size, and this window size should not be less than the update rate we have in the raw data. When querying historical data, Ignition has the option to automatically detect which set of partitions should be used so that we speed up the execution time. After this, we can go in deeper and store our own aggregations, which will allow us to view and analyze aggregations over raw data immediately. And aggregations can be helpful in optimizing SQL queries and Ignition applications with three main things. For data volume, with involving aggregations, we are reducing the overall data volume that needs to be processed and transmitted. That leads to faster query aggregations because all of the aggregations are pre-calculated and stored in the database. We're not doing complex calculations during query execution. And that leads to the third thing, which is overall reduced computational overhead in Ignition. We are doing the custom aggregation using the aggregation pyramid, which is a structure that has several levels, and at each level we have specific granularity. At the top, we have the most aggregated data, and as we progressively go below, we end up with the most detailed aggregations. And these aggregations are configured from the preprocessed partitions, which means that with involving preprocessed partitioning in Ignition, we already have the base of the pyramid. And this pyramid is fully customizable, which means that we can add as many levels as needed and we can change the granularity as each level depending on the use case. The ETL or extract transform load process is done with custom store procedures. And it's important to mention that the levels or the granularity at each level can be viewed as parameter and it can be easily changed. Now, the tag historian used from Ignition uses its own queries for storing and fetching data. But whenever we need to get aggregated data in Ignition, whenever we need to perform data analysis or complex calculation, we need to involve our own queries. And for that, we use best practices for query optimization. Here we have multiple steps that we follow as best practices. For example, appropriate indexes. We involve indexes on specific columns on tables. We maintain the exact indexes and avoid index fragmentation using index reorganize or rebuild. If possible, we are not selecting all columns, but only specific and explicit columns from tables. We optimize the joins. We minimize subqueries because subqueries again have their own execution times. Then we avoid unnecessary functions, and some functions can be replaced and optimized. Then we reduce wildcards because wildcards can end up with scanning the entire tables. And lastly, we use appropriate SQL clauses. For example, when retrieving large amounts of data, we should avoid using SQL distinct. Now let's see a specific use case where we have not optimized SQL query and when we have followed the best practices and end up with an optimized query on the right side. And with this query, we are basically retrieving data for 1 month in a single table. And in the original table, we are using a subquery, we are using case, we do not have indexes on the table. And on the right, we have removed the subquery, we have involved a join so that we can filter on the tag path. We have replaced the case with a specific SQL function. And here we have four SQL metrics which allow us to follow the query execution and performance. And we can see that at the end, from over 1 second, we end up on 13 milliseconds elapsed time. So now to summarize everything, starting with Ignition's main architecture, we have concluded that adding a database is essential for storing data, and storing the historical data in Ignition is configured from Ignition using data partitioning and data pruning. And when dealing with large amounts of time series data, we need to reduce the processing overhead, and we are doing that with preprocessed partitions configured from Ignition and with the customized aggregations that we make. Lastly, we follow best practices to ensure smooth user experience with a particular focus on query performance.